Today's lecture is over 3.6 on conditional probabilities. Today we're going to talk about the use of conditional probabilities to focus on a specific group of outcomes rather than the entire sample space. We're going to understand the relationship between the intersections of events and the probabilities of probabilities, and tree diagrams are really going to come in useful here, and you'll actually be doing tree diagrams on your homework. So we'll talk about them without tree diagrams, and then we'll look at the usefulness of the tree diagrams. So probabilities and polls. In a newspaper poll concerning violence on television, 600 people were asked, what's your opinion on the amount of violence on primetime television? Is there too much violence on television? And here's where the response is. Yes, no, I don't know. They were divided up into men and women. So we get the table of responses here. And from this section, you'll really get an idea how statistics are put together and how they can spin things to make it look a certain way. So out of the 600 people that were surveyed, right, because we have a total of 600 people, we had 418 people said yes, and 140 people said no. So if I just wanted to know the probability of a yes response, it turns out 70% of the time. Doesn't matter if they're male or female. Out of the 600 people, 70% of the time they said violence, that television was too violent. No happened 23% of the time. Of course, we also have an I don't know, so that's why these two don't add up to 100. So what we're going to be doing is looking at a conditional probability. So what if we were asked to find the probability that a woman responded with yes? So the probability that a woman said yes, given that they were a woman. So this is kind of what we're looking for, and we'll talk about this later on. So I wanted to know the number of women that say yes, so the number of women that says yes over the total number of women. So if I look at my chart, 256 women said yes, so I have 256 women said yes out of 320 total. So if I pull up my calculator, 256 divided by 320, that's 80%, which is exactly what we get in our PowerPoint. So that tells us 80% of women responded with yes. So we're going to label them. If I want to know the probability that a woman said yes, that is notated here with this vertical bar. So what comes after the vertical bar is our assumption. So the probability they said yes, given that they're a woman. So this vertical bar reads given that. So if I want to write this up, I say the probability that a person says yes, given they're a woman. The number of women that say yes over the total number of women gives me the probability of 80%. This brings us to a formula, our conditional probability formula. If I want to know the probability of A given B, it's the number of A and B, so the number of elements in both A and B, so the number of women that said yes, over the total number of women. So this is an important formula to notice. I'm going to write on your note card. The probability of A given B is going to be the number of elements in A and B, so A intersection B, divided by the number of elements in B. So using the data, find the following. So given this picture, find the probability that a response is yes, given that the response is from a man. So we're looking for the probability that it was a yes, given that the response is from a man. So I do the number of elements in yes, number of men that said yes over the total number of men. So the number of men that said yes, 162. The total number of men is 280. So 280. So if I plug this in my calculator, I have 162 divided by 280, and I get 57.85. So 57.85%, depending on if they want it in a percent or not. If they don't want it in percent, 0.5785. Round your decimal to a given amount. So we'll put 7. So if it asks to round your decimal, you know how to do that. If they ask you to put it in percent, you move the decimal 2 places. Right? These are the same answers. So 57% of men think violence on television. Television is too violent. Television is too violent. Find the probability the response is from a man given the response is yes. So this is similar, but you have to be careful. Probability the response is from a man given the person said yes. So this is going to be the number of men that said yes. I'm going to rewrite this actually. Sorry, the number of men that said yes over the total amount of yeses. So the number of men that said yes is the same as the number of people that say yes that are men, right? 162. But now this time I want to know the total number of S's. This is the total number of people that said yes. This is the total number of men. Keep that in mind. So this is going to be 418. So if I put this in my calculator, 162 divided by 418, that's 35.76. So 0.30, sorry, what was it, 0.3876, 0.3876, which would mean 38.76% of people that voted yes were men. This is saying 57.85% of men voted yes. So these are two different things. You have to be very careful what they're asking for. What's the probability of a response is yes, and it's from a man? This is not a conditional probability. This is just the probability yes and from a man. So you get 162 over the total, which would be 600, because this is not a conditional probability. This is not a conditional probability here. So you're just doing divided by the total. Conditional probability means you change your total to be the total of whatever your condition is, a man or yes. So here I do 162 divided by 600, so that's 27%. So 0.27 or 27%. So that means 27% of the responses were yes from a man. Yes and from a man. So you have to be careful. Are they asking probability that it's yes given that it's a man, or the probability it's a man given that it's a yes? These are common things to keep in mind. The product rule is going to be from a tree diagram, really. So I'm going to draw a general tree diagram, let's say just A and B. You would put on this branch the probability of A happening. Here you put on this branch the probability of B happening. Then let's say A or B again. So here the probability of A happen, this would be the probability of A happen given A has happened. Here would be the probability B would happen given A has happened. This would be the probability A has happened given B has happened. And this is the probability B has happened given B has happened. Don't get too caught up on the A's and B's here. We'll see an example in a minute of actual cards and actual probabilities. This would be the probability of A. If A happened, then this branch is the probability of A given this branch has happened here. Here, this is the probability of B given that A has already happened. So it turns out you're going to multiply these. So if I want to know the probability of A and A happening, that's going to be the probability of A happening times the probability of A given A happening, right? So it turns out if I look at the branch of any tree diagram, if I want to know the probability of B then A, I multiply those branches. So let's look at actually applying this one. And this is like example 2 in your book and on your PowerPoint. And we're looking at drawing cards. The probability of the first card's a heart, either it's a heart or not a heart. And then after the first card is drawn, we look at the second card and we look at, is it a heart or not a heart? So writing in probabilities here. If I draw a card, I have 13 out of 52 chances it's a heart. Or 39 out of 52 chances that it's not a heart. So now coming to this branch, I assume that I got a heart the first time, so what's the probability I get another heart? Well, that's 12 out of 51, right? And if I drew a heart the first time, the probability of getting not a heart, that's going to be 39 out of 51. If I drop down to this branch, so my first card is not a heart, what's the probability my second card's a heart? Well, I have 13 hearts out of 51 total cards, so it's 13 out of 51. Here, not a heart and not a heart, well, this is a heart, not a heart, so then I only have 38 out of 51 chances for it to not be a heart. So now if I want to know the probability of getting 2 hearts, this would be getting 2 hearts. This would be getting a heart, a card that's a heart, and then not a heart. This would be getting a card that's not a heart, and then getting a heart. This would be getting 2 not hearts. So the probability of getting 2 hearts is 0.06. So 6% of the time you'll get 2 hearts in a row. 19% of the time you'll get a heart, then not a heart. 19% of the time you'll get a not a heart, then a heart. And 56% of the time you'll get 2 cards that are not hearts. So let's look at some examples from the homework. A single dice is rolled. Find the probability of the given events. Rolling a 6. Probability of rolling a 6, same we've done before. There's 1 6 out of a total of 6 dice. Probability of rolling a 6 given that a number rolled is even. So an even number is either 2, 4, or 6. So the probability of rolling a 6, knowing it's either 2, 4, or 6, is 1 out of 3, because I only have 3 even numbers. Rolling a 6, given that the number rolled is odd. Odd numbers are 1, 3, and 5. So 6 doesn't show up here, so the probability of getting a 6 is 0. There's 0 6s out of 3. Rolling an even number, given that the roll was 6. Well, you roll a 6. How many even numbers are there? 1 out of 1, so your probability there is 1. So hopefully this makes sense. The next example has to do with being able to understand the notation. Let P be the event a student passes the course, and S be the event the student studies hard. Write the following probabilities and identify which are conditional and which are not conditional. The probability that a student studies the course given that the student studies hard. So the given that tells you it's a conditional. So we know this is a conditional. So to write this, I want to know the probability the student passes the course given that they study hard. So it turns out my answer would be this one. Is this a conditional? Yes. If it says given that, it's a conditional. Find the probability that the student studies hard given that the student passes the course. So I want to know the probability that they study hard given that they pass the course. So we end up with this example. Is it a conditional? Yes. The probability a student passes the course and studies hard. So this is not a conditional. because it's and. So this would be the probability that the student passes and studies hard. Passes and studies hard. So it turns out this would be your correct answer. A pair dice is rolled. So for the pair dice, you actually have to do this table. For the first dice roll, there are 6 outcomes. In the second dice roll, there are 6 outcomes. So then you fill in this table. 1 plus 1 is 2. So if I roll my first dice, I roll my first dice, I have an outcome of 6 choices. I roll my second dice, I have an outcome of 6 choices. So I fill in this table. Okay, so I filled out this table and I get dice 1, dice 2. So these are my outcomes. This is my sample space. It's not even because I have a much higher probability of getting, say, a 7 than I do than getting a 2, because there's only one way to get a 2. That's a 1 and a 1. But there's 1, 2, 3, 4, 5, 6, 7 ways of getting 7. So now that you have this table, what's the probability that the sum is 12? Well, there's 36 outcomes. So 36 outcomes. So what's the probability that I get a 12? That happens 1 time out of 36. So 1 out of 36. What's the probability the sum is 12 given that the sum is even? So let's find all the even numbers. So I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So 18 even numbers. So what's the probability that it's 12 given that it's even? That's 1 out of 18. There's one 12 number out of 18 even numbers. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. What's the probability the sum is 12 given that the sum is odd? Well, 12 isn't odd, so that's 0. Find the probability the sum is even given that the sum is 12. If you know it's 12, the probability that it's even is 100%, or 1. So keep in mind on this conditional probability, you're limiting the outcome based on any more information. So if you know that the voter was a woman, what's the probability they said yes? That's 80% of the time in this example. So 80% of the women surveyed said violence on television was too much. 80% of the men surveyed, 57% of the men surveyed said violence on television is too much. Together, 70% of people surveyed said violence on television is too much. So you have to be careful with statistics. If your sample space is skewed to maybe more women or more men, and you make a general conclusion, 70% of people say violence on television, there's too much violence on television. You have to be careful because 80% of the women said the television was too violent, but only 57% of the men said violence on television violence was too violent. So hope this little video helps with your homework. If you have any questions, let me know.